The mystery of the final fate of the Voyager probes has been solved. In the absolute darkness of interstellar space, 15.5 billion miles from Earth, two small metallic probes the size of a car continue their escape toward the unknown. Voyager 1 and Voyager 2 don't know they're the most distant artificial objects ever created by humanity. Don't know their radio signals take 23 hours to reach home. Don't even know they've become symbols of a new frontier. If they'd been launched today in the age of artificial intelligence, they'd be talking to us now, perhaps giving us the illusion of self-awareness. But they're just machines, tasked with carrying our flag as far as possible. Nevertheless, as if possessed by a will that so resembles our own, the two probes seem committed to completing a mission that has already exceeded the mechanical limits of their components. And they keep flying, carrying with them the voices and hopes of a turbulent blue world that's now just an invisible speck in the cosmic vastness. That's right, they're still flying out there. But where are they headed? Stay tuned till the end of this incredible video. It was the hot summer days of 1977 when NASA engineers hurled them towards the stars, not knowing they were launching a genuine legend. In the years when John Travolta was dancing in Saturday Night Fever and the first home computers were invading American homes, these two probes began a journey that would challenge every human conception of distance and time. Voyager 2 departed first on August 20, 1977, followed 16 days later by its twin Voyager 1 on September 5th. The choice of these dates wasn't random. It was due to a favorable alignment of the gas giants of our solar system, Jupiter, Saturn, Uranus, and Neptune, which occurs every 175 years. Thanks to these favorable conditions, the Voyager probes could exploit the gravitational slingshot technique, an orbital maneuver that uses a planet's gravitational force to accelerate the probes more than would be possible with fuel alone, greatly reducing the amount needed on board. Voyager 1's primary objective was to visit Jupiter and Saturn and their respective moons, while Voyager 2 was even more ambitious, planning to push beyond and use the gravitational slingshot effect of Jupiter and Saturn to reach for the first time in human history the ice giants Uranus and Neptune. Voyager 1 reached Jupiter in 1979 after nearly 2 years of travel, and then Saturn towards the end of 1980. Voyager 2, meanwhile, reached Jupiter and Saturn a few months after Voyager 1, despite being launched first, because it used a different trajectory that could later take it to Uranus and Neptune. These last two were reached a full 6 and 7 years after the Saturn encounter, testifying to how immeasurably vast the distances between celestial objects are, even for one of the fastest probes ever built by humans. But today, after those remarkable years full of frantic exploration, what's become of them? Where are these formidable discovery machines? Do we know? You bet we do. At the end of June 2025, Voyager 1 was exactly 167.75 astronomical units from the Sun, 4 times the distance of Pluto, equivalent to about 25 billion kilometers or 15.5 billion miles. And it was traveling at a speed of 38,000 miles per hour. Voyager 2, which departed first but took a different route, was at a distance of 140 astronomical units or 21 billion kilometers, and was moving at 34,000 miles per hour along a trajectory that will take it toward completely different stellar destinies. After the primary mission investigating the gas planets concluded in 1989 with the flyby of Neptune, the Voyager probes began the so-called extended phase, the interstellar mission. The orbital maneuvers and gravitational slingshots had accelerated the probes to speeds exceeding escape velocity from the solar system, opening the door to the possibility of launching into the empty space that exists between stars, which, aside from the romantic aspect of pushing the frontier ever further, is also the only direct way to measure the extent of the solar wind's particle influence and thus directly determine the boundary between the solar system and interstellar space. And so it was. Both have crossed that no man's land called the heliopause, where the solar wind no longer reaches and the realm of stellar winds from nearby stars begins. Voyager 1 first reached this milestone, crossing it on August 25, 2012, the exact day Neil Armstrong died, as if the universe had wanted to symbolically mark the passage from one era of exploration to another. Voyager 2 followed 6 years later on November 5, 2018. Since then, the Voyagers have been promoted, earning through field merit the qualification of interstellar probes, having crossed the boundary of the solar magnetic field, where charged particles from the Sun become less important than those coming from the galactic environment. Voyager 1 continues on its trajectory towards the constellation Ophiuchus, while Voyager 2 heads towards the constellation Andromeda. The incredible thing is that we're talking, still after 50 years, about two robots designed way back in the 1960s. Two machines that any research institute would consider hopelessly obsolete today. And in this stark contrast to a collective imagination that still sees them as carriers of Star Trek super technology. If we examine the probes without preconceptions, we can't help but admit we're looking at a metallic structure of modest appearance, though now iconic with the large dish antenna atop the cylindrical instrument housing. The size of a compact car, they weigh 773 kilograms each, of which 105 kilograms are scientific instruments. And they're guided by computers with just 69 kilobytes of RAM, less than what it takes to open a single modern web page. If an alien civilization ever captured one of our interstellar envoys, they'd immediately realize we'd sent them really old stuff. And it's not hard to imagine the faces of some of their technicians as they turned the golden record over in their hands asking, why did they record images on a phonograph record? Yet these ancient electronic brains continue to function perfectly after decades spent in the cosmic void, demonstrating a resilience that would make any contemporary smartphone envious. Their nuclear generators, engineering masterpieces powered by plutonium, were designed to convert the heat of atomic decay into electricity, while the instruments, roughly as old as those used in the Apollo moon landings, continued to record data. Every bit of information they still manage to transmit is a whisper from the abyss, a coded message describing places where human imagination has never reached. But there's something even more fascinating and mysterious about the Golden Probe's destiny. They don't travel alone. Each carries a 12-inch gold disc, the Golden Record, containing a selection of sounds, music, and images from planet Earth. It's our calling card to the universe, curated by Carl Sagan and his team with the same care archaeologists prepare a time capsule for future civilizations. But creating these discs was anything but peaceful. It was a cultural, artistic, and even legal battle that revealed the contradictions and prejudices of human society. On those discs are the voices of children saying hello in 55 different languages, whale songs recorded in Earth's oceans, music by Bach and Chuck Berry, the sound of wind and rain, a baby's cry, and a family's laughter. The Golden Record story begins with a controversy that had shaken NASA a few years earlier. The Pioneer 10 and 11 probes launched in 1972 and 1973 carried gold plaques showing nude figures of a man and woman to represent humanity. The images, drawn by Linda Salzman Sagan, had caused an uproar. Critics had denounced them as pornographic. Feminists were outraged because the man raised his hand in greeting, while the woman remained passive, and conservative groups had accused NASA of sending obscenity into space. The pressure was such that the space agency caved. The representation of female genitals was censored, removing the vertical line indicating the vulva to prevent the drawing from being considered too explicit. When it came to create the Golden Record for the Voyagers, NASA was still traumatized by that controversy. Carl Sagan and his team wanted to include photographs of nude humans to show our anatomy to aliens, but the agency imposed a categorical ban. The result was a grotesque compromise. The disk included only silhouettes of a man and woman without anatomical details, accompanied by a diagram of vertebrate evolution showing some features of the human body. It was as if NASA feared extraterrestrials might be offended by human nudity, a paradox that perplexed even members of Sagan's team. The fiercest controversies erupted around the musical selection. The 20th century in music, the century that had revolutionized sound with jazz, rock, electronic music, was represented by only 3 tracks: Louis Armstrong's Trumpet, Chuck Berry's Johnny B. Good, and Blind Willie Johnson's Dark Was the Night, Cold Was the Ground. No Beatles, no Rolling Stones, no Jimi Hendrix, no Bob Dylan, The Who, Janis Joplin, Jim Morrison's Doors, all erased from the musical history that would represent humanity for eternity. But the most glaring omissions concerned European culture. There was no trace of great Italian opera, no Verdi, no Puccini, nothing from the musical tradition of the country that invented opera. Gregorian chants, a pillar of Western music, were completely absent. Jazz, probably the only American musical genre, was represented only by Armstrong. It was as if Sagan's committee had a selective and somewhat provincial vision of human culture. The 116 images included on the disc created further perplexity. There were photographs of a supermarket, people eating, a violin, various animals, but no Eiffel Tower, Parthenon, or Colosseum. There were no depictions of wars, poverty, famines, or religious conflicts. A conscious decision had been made to represent an idealized, almost utopian humanity. Critics denounced this choice as a lie by omission, arguing that the discs don't honestly represent humanity but only its strangest aspects. The 55 greetings in different languages, heard one after another, could give the impression of a Babel-like planet where everyone spoke simultaneously. To an alien, it might seem like a giant planetary argument rather than a message of peace. The disc also contains hidden messages. In the empty grooves at the end of each side, Timothy Ferris had hand-inscribed a tiny message. To the makers of music, all worlds, all times. And among the sounds of Earth was included a track containing the message per aspera ad astra, through hardship to the stars, in Morse code, a detail that added a touch of mystery to the already mysterious disc content. Hey guys, before moving on, be sure and don't forget to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. There's also a map indicating Earth's position relative to 14 pulsars, neutron stars that serve as cosmic lighthouses with their regular radio pulses. That map will be valid for hundreds of millions of years, much longer than our civilization has ever hoped to exist. But the possibility that the golden records will ever be found and deciphered is, in Carl Sagan's own words, extremely remote. The space between the stars is so vast that the odds of a chance encounter are practically nil. And besides, Voyager 1 and 2 are becoming invisible to the rest of the universe. Their nuclear generators lose about 4 watts of power each passing year. It's like they have flashlights slowly dimming in the cosmic darkness. Voyager 2, however, got a reprieve. Engineers managed to extend its mission until 2026 by tapping into reserve energy from a safety mechanism that regulates the probe's voltage. On October 1, 2024, to conserve energy, Voyager 2's plasma spectrometer was deactivated, though the plasma wave subsystem was kept active. And around the same time, the Jet Propulsion Laboratory had to perform a kind of remote surgery on Voyager 1. When the probe started sending only incomprehensible binary sequences instead of its precious scientific data, teams of technicians stayed up night after night to diagnose a problem in a computer located at a distance equivalent to 167 times that separating Earth from the Sun. They discovered that a single memory chip had failed and had to reprogram the entire system, dividing the software code into fragments and moving it to different sections of memory. all while communicating with a 45-hour delay between command and response. It was like operating on a patient through a phone with a nearly 2-day response delay, but the intervention succeeded. On April 23, 2024, Voyager 1 resumed singing its cosmic songs, and now all 4 of its scientific instruments are working perfectly again. Engineers hope to keep both probes operational with at least one scientific instrument until the end of the decade. But the battle against time is inexorable. By the early 2030s, even the last electronic whispers will cease forever, and Voyager 1 and 2 will become silent ghosts that will continue flying in the darkness for how long? Centuries? Millennia? Billions of years? And indeed, before we ask ourselves where these infinite vagabonds will go when they can no longer tell us their story, we must confront an even more fundamental question. Will they really manage to survive the journey that awaits them? The answer calls into question one of the most persistent myths about space exploration. The Voyager probes aren't immortal as all we believe them to be. Why's that? Well, let's put it this way. Space isn't empty. In interstellar space, Voyager 1 and 2 face a constant battle for survival. As Alan Cummings, a cosmic ray physicist at Caltech who has worked on the mission since the beginning, puts it, "We're dodging bullets out there," Cummings says. These bullets are galactic cosmic rays, charged particles accelerated almost to the speed of light by exploded stars that constantly bombard the probes with destructive energy. In 2010, a cosmic ray probably damaged part of Voyager 2's memory, causing it to send incomprehensible data to Earth. More recently, Voyager 1 went silent for 5 months in an incident that may have been caused by a cosmic ray damaging a computer chip. The difference between light and heavy cosmic rays is like being hit by a golf ball or a bowling ball at the same speed. These high-energy particles can pass through computer chips, altering their code or getting stuck inside, causing permanent damage. NASA engineers had anticipated the hostile environment of space and had equipped the Voyager probes with radiation-resistant components and protective shielding. However, no shield is perfect. You can protect yourself to a certain point, but a particle with enough energy will overcome your defenses, Cummings explains. Near Jupiter, the Voyagers had faced intense radiation, but the particles had lower energy. In interstellar space, the risk of encountering high-energy cosmic rays is significantly greater. But cosmic rays aren't the only threat in this apparently empty but actually populated environment, with about 1 hydrogen atom per cubic centimeter and microscopic cosmic dust particles. Nick Oberg of the Captain Astronomical Institute in the Netherlands conducted an exhaustive study on the probe's future using data from the European Space Agency's Gaia satellite. The probe's surface will deteriorate due to continuous micro-collisions with vast clouds of interstellar dust, though this will happen very slowly, over millions of years. The accumulation of these microscopic impacts will progressively degrade the probe's external structure, damaging the dish antenna and penetrating the internal compartments. The golden record disks, protected by an aluminum case, might outlast the probe itself, but they are too vulnerable to interstellar dust erosion. The crucial distinction is between physical survival and functionality. Scientists estimate the golden records could remain effectively playable for hundreds of millions of years, until surface degradation makes it impossible to read the data inscribed in the grooves. However, the physical remains of the probes could continue to exist for even longer times. According to Nick Oberg, who conducted the most thorough study of their fate, metallic fragments of the Voyagers could survive for billions of years, mute witnesses to an era when intelligence had learned to build machines and launch them towards the stars. But it's purely physical survival. By then, they'll just be space debris wandering through the galaxy, devoid of any functionality or recognizability. Knowing this, we can now ask ourselves, where will these infinite vagabonds go when they become mute? The answer is both precise and terrifying in its vastness. because astronomers have calculated with mathematical exactness the cosmic appointments that await them in future millennia. Here's where the story becomes truly extraordinary, because the fate of the two twin probes diverges spectacularly, taking them towards stellar encounters that will happen when they're already silent relics, and when human civilization might just be a fossil memory buried under layers of terrestrial rock. These cosmic appointments aren't fanciful speculation, but precise scientific predictions obtained thanks to data from the European satellite Gaia, which has mapped with millimetric accuracy the position and movement of over 7 million stars in our galaxy. In 2019, astronomers Corin Baylor-Jones and David Farnocchia published a revolutionary study that traced with mathematical precision the future stellar encounters of the Voyager probes, revealing destinations no one had predicted with such accuracy. Their work demonstrated that space, however vast, is also incredibly dynamic. Stars move through the galaxy like cosmic ships, and some of them are heading towards our stellar neighborhood just as our probes travel toward them. We now know that in 30,000 years, Voyager 1 will completely exit the Oort cloud, that sphere of icy comets that envelops the solar system like an invisible shell, and only then will it have truly left our sun's gravitational domain. During this passage, the probe will cross regions populated by billions of dormant cometary nuclei, blocks of dirty ice the size of mountains floating in the primordial cold at temperatures near absolute zero. Some of these bodies are as old as the solar system itself, frozen witnesses to the formation of the planets 4.6 billion years ago. It will be in 44,000 years that Voyager 1 will have its first true stellar encounter, passing 1.88 light-years from Gliese 445, a star currently located in the constellation Camelopardalis. Gliese 445 is a low-mass red dwarf, just a third of our Sun, dimly shining with a reddish light that would make its planetary system look like a hellish landscape painted in crimson. But from nearly 11 trillion miles away, the star will appear to the probe as a faint but clearly visible point of light, even though by then Voyager 1's optical sensors will have been dead for tens of thousands of years, and the probe will be just a silent metallic relic that won't even know it has reached its most important destination. The most fascinating aspect of this encounter is that Gliese 445 isn't a static star just sitting there waiting for Voyager 1's arrival. This red dwarf, currently 17 light-years away, is actually moving toward our solar system at a speed of 74 miles per second, almost 7 times faster than Voyager 1 itself. It's a cosmic race where the star rushes towards us while the probe goes to meet it, dramatically shortening the appointment time. At the moment of encounter, Gliese 445 will be only 3.4 light-years from our Sun, and will be at that time one of the stars closest to the solar system. This stellar movement transforms the encounter from a simple geometric coincidence into a true rendezvous programmed by the laws of galactic gravity. But it doesn't end there. In 302,700 years, the probe will pass just 0.97 light-years from TYC 3135-52-1, a red dwarf currently located 45 light-years from our solar system. Less than a light-year might mean the probe could even penetrate the star's Oort cloud, assuming it has one. After another 185,000 years, around the 487,500th year of its mission, Voyager 1 will graze HD 28343, a red dwarf currently 35 light-years from us. The encounter will occur at a distance of 1.31 light-years, when both objects will be in a region of space that today hosts only interstellar dust and primordial gas. HD 28343 is a relatively young and stable star, with about half our Sun's mass, and at the time of its encounter with Voyager 1, it will still be in its prime, burning hydrogen in its core with the parsimony typical of red dwarfs. And in an even more remote future, in 3.4 million years, Voyager 1 will pass 1.28 light-years from another red dwarf, cataloged as Gaia DR232, an object currently located 520 light-years from us. Even in this case, its rapid, proper motion through the galaxy will bring it toward the inner regions where our solar system currently orbits, in a stellar journey that will last millions of years and conclude with the encounter with Voyager, or what remains of it. And Voyager 2? Well, in 30,000 years, it too will completely exit the Oort cloud, but from the opposite side compared to Voyager 1. Its trajectory will take it through what astronomers call the galactic South Pole, a region of space where stellar density is minimal and distances between suns are measured in tens of light years. In 42,000 years, having left the periphery of the Oort cloud a while back, Voyager 2 will pass 1.73 light-years from the star Ross 248, located in the constellation Andromeda. What makes this encounter particularly special is its cosmic timing. At that time, Ross 248, today 10.4 light-years from the Sun, will have become our nearest star, being only 3.2 light-years from the solar system, closer than Proxima Centauri is today. Ross 248 is also a red dwarf, the most numerous type of stars in our galaxy, at least 1 billion years older than our Sun. The star is moving toward us at a speed of 50 miles per second, not as fast as Gliese 445, but still enough to significantly shorten the encounter time. At the moment of Voyager 2's passage, Ross 248 will have completed its migration through local space and will have joined our immediate stellar neighborhood. After this appointment, Voyager 2 will continue its journey toward the galactic south, heading for even more desolate regions of space. And in a truly distant future, in 1.97 million years, Voyager 2 will finally have an encounter with a star decidedly different from a red dwarf. We're talking about 51 Sagittarii, a blue-white giant visible from Earth even with the naked eye, being magnitude 5.6, twice as massive as the Sun. It's currently located 265 light-years from us, and is a variable that pulses with a period of a few hours, expanding and contracting with unusual regularity. Well, Voyager 2, in a future when its senders will have long since disappeared, will approach this conspicuous object to within a distance of 2.3 light-years, without being able to record anything, since by then the probe will just be a lifeless relic. Another 280,000 years will pass, and the probe will approach within 1.8 light-years of a small red dwarf, cataloged as Gaia DR296, currently more than 500 light-years from us. That's it. Obviously, we've reported only the closest rendezvous, but these will be the most important encounters the two probes will have from now until 2 million years from now. Between 5.7 and 6.3 million years, assuming they haven't already disintegrated, both probes will exit the local bubble, a cavern of relatively empty space carved out by dying explosive stars, and enter regions where the density of interstellar matter is completely different. They might be slowed by passage through denser cosmic dust clouds, or accelerated by random gravitational encounters with rogue planets, rocky bodies that have been ejected from their stellar systems during violent gravitational encounters and now wander alone in interstellar darkness. Some of these orphan planets could be Earth-sized, rocky worlds that once hosted oceans and perhaps life, now frozen at temperatures of minus 418 degrees Fahrenheit, while drifting aimlessly through the cosmic void. The first major cosmic milestone will occur in 200 million years, a time so long that on Earth the continents will have completely changed shape. New mountain ranges will have risen and been leveled by erosion, and animal species unimaginable today will have dominated the planet. At that moment, our little envoys will complete their first circuit around the center of the Milky Way, becoming true galactic navigators. They'll be ancient relics of a civilization that perhaps no longer exists, but they'll continue their elliptical orbit through spiral arms that will form and dissolve like cosmic waves. During this first galactic orbit, the probes will cross all the major environments of our galaxy. They'll pass through the Perseus arm, a region rich in young stars and bright nebulae, where star formation proceeds at an accelerated pace. They'll cross the Sagittarius arm, where some of the galaxy's oldest stellar complexes are found, suns that have been shining since the universe was young. But by this point, after hundreds of millions of years of exposure to cosmic rays and interstellar dust erosion, the probes will be reduced to unrecognizable metallic fragments, silent relics wandering through an ever-evolving galaxy. However, the physical remains of the probes could continue to exist for even longer times, mute witnesses to an era when intelligence had learned to build machines and launch them towards the stars. Our messages to aliens will have long since been erased by cosmic erosion, but the metallic debris of the probes might still float in darkness when our sun has died and Earth has become a dead world orbiting a white dwarf. At this point, one question remains. Sagan believed there was zero probability that some alien civilization would manage to intercept one of the probes, only to rack their brains trying to figure out what the hell that primitive golden record inscription could mean. Okay, but is there a way to make sense of this zero? Well, we could try. To begin with, we need to set some limits, like the probes will remain intact for, let's say, 5 million years. Maintaining their current speed, this means that in this time interval, they'll manage to travel 650 light years. Now, the latest studies state that based on certain assumptions we're about to analyze, the number of technologically advanced civilizations present in the Milky Way is close to 36. And this means the average distance between these civilizations is about 17,000 light years. Starting from this premise, the authors investigated, based on different scenarios, the probability that our galaxy hosts planets inhabited by beings capable of exercising control over the space around them. The first scenario assumes that intelligent life arose wherever it was possible, on rocky planets located in the habitable zones of stars with the right age and the right distribution of metallic elements, and that it lasted for the entire lifetime of the parent star. This loose criterion returns an estimate that's not very useful to us: tens of billions of potential habitats. The second scenario, more limited, assumes that, just as happened for Earth, life forms between 4.5 and 5.5 billion years after the birth of the parent star. Surprisingly, this filter seems to reduce to a number between 4 and 211 the possible civilizations within the Milky Way capable of communicating with others, and in this range, the number 36 seems to emerge from the series. It's an estimate, of course, and a conservative one at that, if only because it's based on the fact that our civilization has been capable of sending signals into space for barely 100 years. It's also a bizarrely normal number. If we have to take it at face value, then we could arrive at the final question. What are the chances that a small, now inert probe could be identified by a civilization that has full control of an area equal to that of a disk with a radius of 17,000 light years? Well, Sagan was right. The answer can only be zero. Does this mean we must give up overly romantic dreams and the science fiction that takes the place of reason? Not really. Dreaming is always good, and there's no reason to stop. What needs to grow is the awareness that in a universe where everything is born, evolves, and dies, where stars explode and new solar systems form, where time flows relentlessly, erasing every trace of the past, the Voyager probes represent something unique: the will of a species to leave a mark in the cosmos, even if no one will ever be there to see it. This is the true mystery surrounding the final destiny of the Voyager probes. Not where they'll go, but what they'll represent when everything we know has changed beyond all recognition. They are our bravest children, launched toward a future we'll never see, carriers of a message that may never be received. But their journey continues, and we want to imagine it can continue for hundreds of millions of years, long after the last human being has closed their eyes and the last light has gone out on Earth. In the glacial depths of interstellar space, two small metallic probes will write the last chapter of human history, a cosmic epilogue that will last longer than anything else our species has ever imagined.